Thanks for the invitation. Yes, so we're going to switch gears a little bit. This is going to be a theory paper, but on heterogeneous agent models, of course, so it fits the topic in that way. So this paper is on, as Stefano already said, existence and uniqueness of recursive equilibria for models where we have both types of risk. Idiosyncratic risk, so we get the cross-sectional distribution, we have heterogeneity, and also aggregate risk. And why is aggregate risk so difficult to handle? The reason is that once you have your cross-sectional distribution with aggregate risk, of course, we don't get kind of a stationary distribution as Ayagari would kind of suggest, but the distribution will be bumped up or down depending on the aggregate risk. And then the distribution itself becomes a state variable of the policy functions. So here, this model, this paper really looks at the standard model which we teach in the PhD macro curriculum. So it's the Ayagari-Bewley economy with idiosyncratic risk, and then in addition to that, aggregate risk, so it's this Kruse-Smith model. And then for this model, of course, closed form solutions do not exist. And then the question is, okay, do solutions actually exist? And if yes, how can we compute them in the best possible way? So there is some existing literature, which in the theory, economic theory literature, which also looks at that type of model, but all of these papers always have some slight modification of the standard model that more applied macroeconomists would use to investigate research questions. So one of the two ways of how to make it easier theoretically is, of course, you assume a bounded utility function. But then, for instance, when we want to look at the CRRA utility, that's not bounded. Or instead of the standard continuum of agents that we would like to assume, some of these papers assume that there are finitely many agents. And also, some other papers, like, for instance, the work by Brum, Kübler, and co-authors, what they do is they show existence of a recursive equilibrium, but then the policy functions in that recursive equilibrium have some additional state variables, like a sunspot, for instance. And here, in contrast to that, I really want to look at the minimal recursive state space, which is really the type of equilibrium that we would compute with like a Kruse-Smith type algorithm. All right, and then of course there's also some work on idiosyncratic risk, where we do not have aggregate risk. And there are even some uniqueness results, but there the uniqueness results only appear when we assume that the risk aversion is smaller or equal than 1. So there are some limitations there. So I try to contribute to this literature with this paper. I really want to look at policy functions with a minimal state space. So here, for instance, if we have an optimal consumption function or an optimal savings function, that would depend on Z, which here denotes the aggregate shock, epsilon, which denotes the idiosyncratic shock, X, which denotes the current savings, or whatever your model has, savings, bond holdings, whatever you would like. And then mu here denotes the cross-sectional distribution of the agent-specific variables. And so the way that I approach this problem theoretically is that I essentially try to state this large model as a convex optimization problem. And doing so, I kind of want to simplify this continuum of Euler equations. So we have a continuum of agents, we get a continuum of Euler equations. I simplify this continuum to one functional Euler equation. And then also the market clearing conditions will play a role, so that I kind of come up with one equilibrium operator which summarizes all the first order and market clearing conditions. And then showing that using this operator we can actually translate everything into a convex optimization problem, I leverage results from the convex analysis literature to show that indeed we get existence, in the sense that we get a root to the first order equations. And because we have strict convexity, I can also show uniqueness. So that's essentially kind of the paper in a nutshell. So now let me give you a preview of the methodology, so that after this first few slides, you know what's going on. And then if it's not your cup of tea, maybe the details are not that interesting to you. All right, so here, what I want to do is essentially, I want to show that this whole problem with continuum of agents, we get this cross-sectional distribution, which is state variable. So the space of distributions enters the policy functions, and that's an infinite dimensional space. So everything is actually very complex, but I actually want to reduce it to this simple picture. So here, when we look at this function f, you can see that this is a convex function. And then essentially, I want to come up with this function m, which is essentially the first order derivative of f. And then, of course, convex analysis tells us that we can find the minimum of f if we look for the root of m. So that would be the necessary condition for optimality. And then the sufficient condition is that this function m needs to be monotone. And then we know that, indeed, we have found a minimum. Also, if this function is strictly monotone, we know that the minimum must be unique. All right? So that's just really convex analysis 101. And that's what I want to reduce the whole problem to. So in the end, what I get for this function m is an equilibrium operator. So I construct all the necessary conditions of the equilibrium, which is the first order conditions of households, so the Euler equations, and the market clearing conditions, and thirdly, the consistent law of motion of the cross-sectional distribution. So out of all of these three items, I construct an equilibrium operator m, and I show that this operator is monotone. All right, so that kind of gives me this generalized first-order function or operator. And then essentially I have to show that, well, if it's a monotone function, I want to find a root of this function, right? And there I can use a generalized version of the intermediate value theorem, which tells me that, well, if you find a candidate policy at which this operator evaluates as negative, if you find a candidate policy at which it evaluates positively, then there should be a zero, right? And then I actually don't need to know what h at 0, so this optimal equilibrium policy looks like. I just need to find candidate policies which are admissible at which the operator evaluates at different values. Okay, so, oh, by the way, I should say that here, this equilibrium operator, I construct for the case that we do not have any borrowing constraints, all right? So I do that first, and then I extend it to the case that we have borrowing constraints. And the way I do this is that I use the first order condition which I get for the case without borrowing constraints. And because this is monotone, I can actually construct an objective function f from this operator m, which essentially has m as its derivative and is minimized exactly where the root of m is. So it has these features, and I can construct f. And the moment I can construct f, I can, of course, attach the borrowing constraints to this objective function with a Lagrange multiplier approach.
But then could it be that f is not continuously differentiable?
I make assumptions so that it is. Yes.
No mass points.
Oh, there will be, in the distribution, you can have mass points. Yes. In the distribution, you can have mass points, yes. Yeah.
But now you have also a distribution of Lagrange multipliers.
Yes. So the Lagrange multipliers will have exactly the same form as the policy functions.
Okay.
Yes, exactly. Yes. All right. And then lastly, what I get out of this convex analysis part here is actually also I get a convergent algorithm, which is guaranteed to converge to the solution. But as I said, this is more of a theoretical algorithm saying that if we could represent on a computer the distribution perfectly, so without any approximation error, then we get convergence of this algorithm.
Should I think of m?
Yeah. So that's essentially the methodology, and now I'm going to dive into more details. So first I'm going to present a generic model so that we're all on the same page. Then I want to show you how I come up with this operator m, with this first order condition. So there, as I already told you, I have to switch from distributions to random variables. And then I will show you how I get this equilibrium operator. And then once I have this operator M, I just need to show, I need to apply this generalized intermediate value theorem. So that's what I'm going to discuss here. And then lastly, what is the iterative procedure which leads to the equilibrium if we want to compute it. And then I'm going to show you some examples, namely the Cruiser-Smith model and also the Haggard economy with aggregate risk. So in the Haggard economy, that is an endowment economy with bond trading. So there we actually need the zero net supply condition for bonds. All right, so in the generic model, I kind of have a model where I can have both the capital market and a bond market. So here, the exogenous variables, we have the aggregate shock, so that's aggregate TFP, and then we have the idiosyncratic shock, that's the labor productivity, and the distribution of the labor productivity shock can depend on the outcome of the aggregate shock. So for instance, it would be more likely to be unemployed if you're in a recession. Then for the endogenous variables, that's the standard ones, consumption, capital savings, bond holdings. These are the aggregate wage and rental rate prices of the capital market. And then we have the bond return for the bond market. All right, so for the individual problem, that's also very standard. So all agents optimize a time-separable utility function. It's a CRA utility. So here gamma is the risk aversion parameter. Beta is the subjective discount factor. And then the budget constraint is fairly straightforward. So on the plus side, agents receive some endowment. So here I kind of combine the Cruiser-Smith model with Haggard economy. That's why I have both endowment and labor income. But then you could also split it again if you wanted to. So this is the endowment. This is an exogenously given process depending on the shocks. We have the labor income part. So here the wage is really just coming from a Cobb-Douglas marginal productivity of labor. L, here I only look at exogenous labor. So L is exogenously given and determined by the shocks. All right. I'm currently working on an extension where I want to introduce endogenous labor choice. It's also possible, but I still have to write down all the details. So I'm not going to present that yet. Right. So now I want to look at recursive equilibria. So I want to look at individual choices as functions of the variables I already discussed. So the exogenous shock, here actually epsilon is missing, sorry for that. Savings, bond holdings, and then the cross-sectional distribution. And then the returns are also functions which look similar, but these do not depend on the agent-specific variables. So here they just depend on the aggregate variables. So we have Z prime and mu prime, so the exogenous aggregate shock and the cross-sectional distribution. Here for bond holdings, I specifically let it not depend on the aggregate shock because the bond should be a risk-free asset. So actually the return is already determined in the period where agents buy the bond. Right? So you could either have it for a bond price and then the bond pays out 1, or you have a return and, I chose to do it with the return, but then the return is essentially predetermined in the previous period. Now, also, we need that the law of motion of the cross-sectional distribution is consistent with individual optimal choices. So what this means is that essentially, when we apply the optimal choice of the agent K prime and B prime, then we compute the cumulative distribution function. So we count how many agents have K prime and B prime, but below a certain level, right? That will be the probability of having K prime and B prime below that certain level. That needs to be consistent with the individual choice. All right. And then here also you can see that there are 2 steps. So first of all, we average over the beginning of period cross-sectional distribution. But then also when we go to the next period, so essentially here we have the end of period choice. We average that end of period choice with beginning of period distribution. That gives us the end of period distribution. And then still to go to the next period, beginning of period distribution, we still get this mixing because the idiosyncratic state for some agents will change. And therefore, we have this additional averaging over the new idiosyncratic states. All right. Okay, so one of the important assumptions that I need to make here is that everything is square integrable. So all the exogenous processes need to be square integrable, and also all the exogenously given functions, so for instance the endowment function or the labor supply function, need to be square integrable, meaning that they have finite variance. But that doesn't really make, in my view, that's not a strong restriction, because for instance, we can still look at productivity processes which are finite Markov chains or AR1 processes, and the typical ones we would choose. All right. So now, how do I come up with this increasing function m? First of all, I have to go from distribution to random variables for the reasons that I have already explained. So I need to be able to take derivatives with respect to the future distribution, because that will depend on today's optimal choices. And therefore, to take derivatives with respect to the distribution, I need to look at well-defined directional derivatives. So here, this is why I switched to random variables, because the random variables are a well-defined Hilbert space, especially the square integrable ones are very nicely behaved. All right. So, or in other words, if we look at the difference between two random variables, that itself is a random variable, and therefore everything is nicely defined. So what I'm going to do is I'm going to rewrite all the functions which depend on mu as functions which depend on m. So here m is just a random variable which is distributed according to the distribution function mu. And also, of course, I need to translate the consistent law of motion from the distributions to the random variables. But this is actually quite straightforward. So first of all, I told you we have those two steps. We start with the beginning of period distribution. We go to the end of period distribution after all agents choose their optimal savings and bond holdings. And then we go to the next period beginning of period distribution when the new idiosyncratic shocks realize. And so these are the two steps I do here. I can do exactly the same with random variables. So given that we start with a multivariate random variable, it's multivariate because of course it's the idiosyncratic state and the savings bond holdings. So here we have a multivariate random variable which is distributed according to mu. I go from the beginning of period to the end of period by just applying the optimal policy function of savings to this random variable. So instead of the agent-specific savings, I actually insert the random variable of beginning of period savings into the optimal policy function, into the optimal savings function. Then going from the end of period to the new period, I essentially paired with the new idiosyncratic shocks. So I get a new multivariate random variable at the beginning of next period here. And then as you can see here, this multivariate random variable will, of course, depend on the optimal policy functions of the agents. Right? So that delivers this consistency.
Chi is what?
Chi is now kind of the savings random variable. So capital savings and bond holdings. But what you can see from here is actually when we go forward multiple periods, then we always have to apply the optimal policy function. So we actually kind of get a composition of optimal policy functions. And in the end, the random variable at the future time point will depend on the time history of the exogenous shocks. All right. However, there's actually a way of resolving this, because I want to look at recursive equilibria. Something like that doesn't really play out well, right? Because here I would need to keep track of the whole history. But then I can actually more smartly define the probability space, or more specifically, the sigma algebra of the probability space. So I just look at particular sub-sigma algebras of this full information sigma algebra, where I specify that the agents have to forget the history. All right, so I just look at the random variables which are measurable with respect to this specific sub-sigma algebra where the agents forget the history. So, all right, so then I already told you that M are actually these functions and that I can use this specific outcome as an agent identifier. And so this is essentially how I rewrite my policy functions. So I started out with policy functions which looked like this. So here we have the aggregate shock, the idiosyncratic shock. These are the agent-specific current states, current savings, and the cross-sectional distribution. So now here I already insert the specific outcome space for that agent I'm looking at. And what this tells me is, okay, this policy function actually depends on two things. The random variable m, which has the distribution mu prime, and omega. And therefore, I rewrite the policy as depending on the aggregate shock, this outcome omega, which identifies my specific agent, and the random variable m prime, which is now this function, right? So m actually specifies the whole class of agents. And if I evaluate m at the specific outcome omega, I actually get a specific agent, right? All right. So when we look at this, here what we can see, the policy functions are now also functions of omega, so they are actually exactly of this form, right? So they are random variables themselves. And more specifically, they are random variables themselves, which have another argument, so they're indexed random variables. Indexed random variables are, of course, stochastic processes, right? So for different indices m prime, I get different random variables. And that's why these policy functions, so now I have a space of policy functions which are actually general stochastic processes. Okay, so now how do I get to this first order equation, this function m which is increasing? So I actually start with the Euler equation of the agents. So here, this is really what it is, marginal utility today, marginal utility tomorrow, taking the expectation of it, of course, and then weighted with the return that we could earn. Then also we have the budget constraints for consumption today and consumption tomorrow. And of course also these are actually two Euler equations. We have one for capital savings, one for bond holdings, right? So that's actually the index J here. All right, so now the first thing that I do is that I look at these agent-specific K and B, and I replace this with my random variable chi, all right? So with my random variable of capital holdings and bond holdings. So this is what I do here. So everywhere where there was K and B, now I have chi K and chi B. So these are the random variables. Also, instead of K prime and B prime, I already substitute the optimal policy function, which is now also a random variable.
What is y prime? It's your Lagrange multiplier on the create component?
Yes, yeah. For now, I keep y prime to have the general problem, and then I will actually look at two cases: one where y prime is 0 because we have no borrowing constraint, and one where it might be non-zero. All right. Also note here that, of course, when we look at consumption tomorrow, here I already have to concatenate the optimal policy with tomorrow's distribution or tomorrow's random variable. And tomorrow's random variable itself, of course, depends on today's optimal choices, right? So there I need to keep reapplying that essentially.
Why do you need the equation 2 and 3? Because
these two?
2 is budget constraint, at the, let's say at the t.
Yeah, and that's the budget.
Is at t plus 1.
Yes, yes.
But it's only the update of.
Yeah,
the 2 at the same time in your.
The reason is that I actually already plug in the right-hand sides into these equations, into the Euler equations. So I don't keep track of the budget constraints separately. I already plug them in, but I refrain from doing it on the slide because then it gets really messy, right? Okay. So. But that's the idea, yes. I want to plug in as much as I can already into the Euler equation.
So each individual is only now one realization of M.
Yes.
And one equation.
Yes, yes, indeed, indeed. Absolutely right. So then the next step is that I also want to plug in the market clearing equations that I can already plug in. And that's for, of course, here the capital return and then also for the wage. I can already plug in that these are the marginal productivities. So that's what I do here. And then, of course, the marginal productivities depend on the aggregate capital, which is the mean of the capital distribution, right? So this now also depends on the random variable. It's the mean of the random variable. And when we go one period further, it's still the same thing, but of course that's the next period random variable. All right. Here for, let me see, for HR I do the same here, right? So I already plug in the marginal productivity for the capital return. Where I can't do this trick is the bond return, because there I don't have an explicit formula for the bond return. So I need to keep track of the bond market clearing separately from this Euler equation, which already contains all the other equations. All right, to summarize, what we had on the previous slide now gives me this Euler equation operator, where I already plug in the random variables, the policy random variables, and the returns from the capital market. In addition, I have this bond market clearing operator. So here I just average over the optimal bond holdings of the agent, and that, of course, has to be equal to 0 in equilibrium. Also note that here I take the minus of that, because here I also take the minus of the Euler equation. The reason being that in economics, of course, we want to maximize, but in the maths literature, people minimize, so I kind of switch the signs just to get the minimization. All right. So now I have these two items, and combining them gives me this general first order condition. All right. So now I have essentially a vector of the Euler equation operator and the bond market clearing operator. And then I want to find a root of this operator, and that will be my equilibrium. Now that we have this equilibrium operator M, which contains all the equations we need for equilibrium, I use the theorem by Rockefeller, which essentially says that if M is maximum monotone, so it's increasing in this picture, then there exists a subset on the domain of that operator. So if we look at the x-axis, we can find a subset such that 0 is in the interior of the convex hull of that subset of the domain. And if this is true, so if we can show the two things, maximum monotonicity, and that this condition holds, that we can find the 0 within the convex hull of the interior, or the other way around, the interior of the convex hull of the domain, then there must exist an optimal policy which results in the root of that operator. And so this is really this intermediate value theorem. So here, if we look at this, if we can find a subset of the domain B where we have a positive evaluation and the negative evaluation, if we take the convex hull of those 2 points, of course, then the 0 should be within. All right. And then uniqueness, of course, naturally follows from strict monotonicity. So if, in addition to maximum monotonicity, we can show that we have a strict monotone operator, we get uniqueness as well. So now my strategy is to show maximal strict monotonicity of this operator M, first of all. So that's the first thing I need to do. And that I do for this general model I showed you, where we have bond trading and capital markets. Then this second thing, that I show that there are two candidate policies and we can find a 0 in the interior of the convex hull. That I actually do for the example models. So I use the Cruiser-Smith model, and I use the Haggard economy with aggregate risk to show that indeed we can find a subset of the domain so that we can construct this 0. So here, in the end, the second condition essentially will give us sufficient conditions of existence and uniqueness for these specific example models. And these will be conditions on the parameters of these models. And that will ensure that the equilibrium that we look at here, the recursive equilibrium, is an interior solution. So it's not an outer key equilibrium. Okay? So that will come out of this condition, which I show for the specific example models. All right. Now, but first, let's show monotonicity. And here, I indeed do it in 2 steps. So first, I look at the operator without borrowing constraint, and then I add the borrowing constraint later on. Let's see, how much time do I have left?
But if you have autarky, you have no unicity, uniqueness.
Pardon?
If you had autarky, you would have no uniqueness because prices will not...
Exactly, yes. So then I have the, that's why I have these interiority conditions. Indeed, absolutely, yes. So if these conditions are satisfied, then there is a unique interior equilibrium indeed, yeah. All right, so first looking at the unconstrained case, the way that I show maximum monotonicity is essentially that I restrict the set of policies that I look at. Well, the restrictions are more or less strict. So positive consumption is, of course, natural. Also, I need the consumption increases on average. So that's an aggregate condition. It's not for the individual. Increases on average with higher cash on hand. I guess it's also not really that big of a deal. That bond returns decrease with higher aggregate bond demand. So that's also an aggregate condition, not an agent-specific condition. I need continuity and differentiability in the random variable M prime, and concavity of consumption in the random variable M prime, and concavity of the log bond price in M prime. Let me maybe briefly talk about the convergent iterative procedure, and then let's get to the example models. These are more interesting, because there I can show you parameter conditions for these models where you get existence and uniqueness. All right, so what this model gives me also is that if it kind of gives you a computational algorithm saying that if you start with a guess of your optimal policy functions, it delivers you kind of a way of how you should update that guess in order to converge to the true equilibrium policies. And the way this works is, let me go here, is actually using this operator. And what it does is that, so this is the operator we need to update. This is our old guess, and this would be our updated guess. So here n is just, how many iterations did I already do with the algorithm. Now, how can I interpret this operator? I can actually interpret it as minimizing this objective function that I showed you earlier, which belongs to this equilibrium operator. And then this is, in addition, I have a regularization term. And this regularization term essentially ensures that this update doesn't go too far into a direction so that we don't get this divergent behavior. And so here this is kind of similar to a value function iteration in the sense that in each iteration I have to optimize again. All right? And so in that sense, it's kind of similar to value function iteration, the flavor of it. But this algorithm is
still not the same as showing that it's contraction.
No, indeed, because what I have here is essentially non-expansiveness. So this operator, this one, is a non-expansive operator, so that means Lipschitz constant 1. All right, so it's not a contraction, but it's not that far away from a contraction. And essentially this regularization term ensures that even though it's not a contraction, we will converge. That's why the regularization term is there.
Is the regularization term important to be sure that you remain in the square integrable?
No, that is actually already done if you just use the kind of the Euler equation. Yes, yes, indeed. And so here, this is then really the Lagrangian, and if you put in this Lagrangian into this updating, then you get a converging algorithm. All right, so let's jump to the example models. So first of all, I look at the Kruse-Smith model, so scrap the bonds. We just look at capital savings. So that's really the standard model. All right, here, the exogenous labor supply function, that's why I kind of write it like that. Here, I actually already deviate a little bit from the original Kruse-Smith paper in the sense that I have an unemployment insurance policy, which is kind of a zero sum, right? So the employed pay a little bit, but therefore the unemployed get a little bit. And that's why I have a slightly more complicated labor supply function. All right. Then market clearing is, of course, the standard one. So we take the average of the cross-sectional distribution. And the sufficient conditions I get for the interiority equilibrium is the following. So if we have a risk aversion larger than 1, I have a joint condition on the discount factor of the agents, the capital depreciation rate, and the risk aversion. So now here, of course, if gamma is smaller equal 1, then this condition is always satisfied. But if it's larger than 1, then you kind of need to restrict either discounting or the depreciation in order to get existence and uniqueness. And then for risk aversion less than 1, at risk aversion equal 1, I don't need any further restrictions. But for risk aversion less than 1, I need kind of a minimum productivity and a minimum initial capital. And the reason being is that for the whole state space, meaning all possible distributions you could observe in this equilibrium, I have to prohibit the agents to prefer the autarky equilibrium. And this is why I have these conditions. Otherwise, without these conditions, in certain parts of the state space, the agents would prefer the autarky equilibrium if these conditions are not not met. All right. So this is for the Cruiser-Smith model. So here I would also think that this condition is fairly new because uniqueness we previously only got for the Iagari model, risk aversion less or equal than 1. So I think that's already an extension of that. Delta is the capital depreciation rate. Yeah. Yes. Yeah. That's right. So it kind of incentivizes agents to at least save a little bit, right? So if, for instance, if capital depreciation is fairly high, what I want is I want to prevent exploding returns, so capital going to 0. So I need agents to save at least a little bit. Minutes, I guess. So, and here, for these example models, that's exactly this condition what I said. You need to show that you get a candidate policy at which the equilibrium operator evaluates positive and a candidate policy at which is evaluates negative. And the way I do it here is really just, I look at aggregate cash at hand, then I have a parameter here, and I let the parameter go to 1 or go to 0. And that means that agents either consume all of the aggregate cash on hand or nothing of the aggregate cash on hand. So it's kind of this extreme strategies. All right. And then if agents consume nothing and save everything, then I get a positive Euler equation evaluation. And then, of course, in the other case, I get a negative value for the Euler equation. All right. And then the last step in the proof is essentially, now that I have those two policies, I still need to construct this convex hull, and I need to show that the 0 is within that convex hull, and that I do as well. Okay.
So how do you have an explicit construction?
Well, the way is essentially, the way I do it here is because these policies are constructed such that the random variable or the distribution only shows up as aggregate capital and aggregate labor. This kind of gives me a very simple dimension for the random variables. So I look at all possible outcomes of random variables, which would mean all possible outcomes of capital. So capital from 0 to infinity. And at all these possible outcomes, I, of course, get a function t over this whole space of outcomes. And this function over this whole space of outcomes will be consistently positive if we consume nothing, and it will be consistently negative if we consume everything. So check it at every given point in the state space, essentially. And at every given point in the state space, given the sufficient conditions, this is strictly above 0, and this is strictly below 0 at any given point in the state space. And therefore, at any given point in the state space, in the convex hull, there must be the 0. And that's essentially how I construct this convex hull. And that's also why I need these conditions, because if these are violated, then there are points in the state space, so outcomes of the distribution eventually, where agents would have both of these cases either below or above 0. Right? So then I couldn't show that indeed the 0 is inside the interior of the convex hull. Or in other words, in some states of the state space, agents would prefer the autarky equilibrium to the interior equilibrium. So if these conditions are satisfied in your model, then you know that the equilibrium that you compute should satisfy the admissible set conditions, which I had here.
Okay. And the bond return?
Yes. Well, I mean, for the Cruiser-Smith model, we don't have the bond return. So then everything related to capital market and consumption, yes. And then also lastly, I looked at the Aggregate economy, which is the model where we just have bond trading and an endowment. And the endowment is exogenously given. And here bonds are in zero net supply. And so here the sufficient condition that I need is really just a condition on the average endowment. And the average endowment, if we took the minimum of the average endowment over all aggregate shocks, that needs to be greater or equal to 0. Well, that's not a big restriction. And then, of course, the maximum average endowment, if we take the maximum over the aggregate shock, that needs to be finite. But I would also argue that this is not a very strong restriction. So here for this Aggregate economy, I would even think that this is not really that strong of an assumption to make. All right. So maybe... No, for the Aggregate economy, not. No, it's really just a condition on the endowment process. Yeah. All right. So to conclude, that's the theory paper on heterogeneous agent models where we have aggregate risk as well. And so also what I'm currently working on is actually also an extension to have endogenous labor decisions. And then also naturally, I want to apply this also to kind of Ramsey planar problems, because of course there, if we look at the Ayagari model and we don't know whether a steady state exists or not, then of course we need the dependence on distributions to evaluate whether we can find a steady state. So that's something I'm working on right now, but I don't really have the results yet to present. So, all right. Thank you.